Right, so thanks everyone for joining us today for our Blue Bag. Today we have Barney Austin and Frank Schalla from Aqua Strategies. I think Barney said that Frank was going to be mostly talking to us. They're gonna tell us about a project that they're doing, partnering with us to do this project on reservoir firm yield uncertainty. And Frank, I guess you'll tell everybody, because a lot of people that might be watching or later watch this might not know, what that means. And then I've also asked them to talk a little bit about, when they finish that, it's a small project, and when they finish up telling us about that, I've also asked them if they would tell us a little bit about other things that they think might be interesting to projects for, to partner with them on. So, with no further ado, Frank. I guess, Frank, I didn't really introduce you. So do you want to start off introducing yourself a bit, or maybe Aqua Strategies or whatever? I mean, I know you've both talked to us before, but yeah.
Yes, sure. Unless Barney wants to. He will be talking about the first couple slides.
Oh, okay.
Frank's way too modest, so let me introduce us. So I'm Barney Austin with Aqua Strategies, formerly with the Water Development Board and another consulting firm called Interra. Aqua Strategies been in place since 2014, and we do cool H&H studies primarily. And Frank Schalla was our first employee. He is a UT graduate and just a kick-ass civil engineer who's taken the lead most recently on all our water availability studies. So yeah, why don't we jump into the presentation then? So the objective of the study is to characterize the uncertainty in reservoir firm yield from normal hydrologic variability. And as Mona pointed out, some folks might not know exactly what firm yield is on a reservoir, but it's a super important term in the water supply planning world. And what it is the amount of water, normally on an annual basis, that can be diverted from a reservoir through a repeat of the drought of record. So let's assume we get the drought of the 50s or the drought of 2011 to 2015 again. How much water can you withdraw from that reservoir on a consistent basis from year to year without the reservoir emptying out? And that's what we call the firm yield. And traditionally in Texas, we have a set of water availability models called the WAMs, which run on a monthly time step. And we use these models, and there's a different model for each basin, each major basin in the state. We use these models for determining the firm yield and also the reliability of water rights and the opportunity for additional water rights and reliability of all of those water rights. And so there's been questions, particularly those concerned with climate change, about what that firm yield really ought to be, because in Texas, for the convention has been for the past couple of decades at least, is to plan based on what's happened hydrologically in the last 50 or 60 years and assume that there isn't going to be a drought any worse than that in the next 50 or 60 years. And that may not be a good assumption to make. And so there's different approaches that could be taken to estimate firm yield under climate change situations. But in this particular study, maybe we should jump to the methodology slide, Frank, the next one. What we're doing here is taking all of that historical hydrology and reshuffling it and extending it and making a really long time series of flows, reshuffling, like I said, in a number of different ways, and then rerunning that reshuffled hydrology back through the WAMs to see if there are situations where there'd be plausibly a drought worse than what we've seen historically. And so we use this Markov-Chain Monte Carlo approach to generating 100,000 years of hydrology based on the naturalized flows that are in the WAM. And we use that time series of information, like I said, and run it through the WAMs again. And when we do that, we analyze those 100,000 years of record first and pick out new droughts. So when there's a severe drought because of the sequence of hydrology, we isolate that particular drought and then rank it compared to all the other droughts that have occurred in that 100,000 year period of time. And then we're recalculating the firm yield based on that hydrology. The reason this approach...
Before you go on, could you explain to people what synthesized and naturalized stream flow are, and then what the significance of the 100,000 years is?
For sure. So naturalized flow is the flow that would have occurred without any anthropogenic impact. So no return flows, no diversions, no reservoirs, nothing basically. What the flow in those rivers would have been if we weren't affecting them in any way. And that is the main input to the WAM. So those time series have already been generated. What engineers and scientists have done is gone back through the historical hydrology and effectively added back in diversions and taken back out return flows and removed the effect of reservoirs so that we get to the best extent we can a naturalized flow time series. And that's the starting point for the WAMs. The synthesized stream flow data, what I'm talking about there is the 100,000 years of flow that we've created through this Markov-Chain Monte Carlo approach. And that's what we're using for these studies. And there's Frank's going to go into the details on how that's done and sort of the statistics of all of that and justifying that approach later on in the presentation. But this is kind of an alternative approach to using some climate model results and estimating rainfall runoff and generating a new time series of flows for input into the WAMs. In this situation, we're actually using flows that have been observed in the past. We're just shuffling the order that they occur in. So from some perspective, some people think this is a much more realistic way of estimating what that worst drought could be rather than relying on a climate model and a rainfall runoff model to generate those naturalized flows, because there's a lot of assumptions that go into those climate models, of course. And I should have pointed this out before, but what we're doing here is a continuation of the work we were contracted to do for the Texas Water Development Board. And we got about, I don't know, halfway or 2/3 the way through that project. And I gather what happened, some of our project partners, river authorities in the basins we had chosen, got cold feet and were worried about what those results would show and whether those contracts that they had executed with their customers were as reliable as they portrayed them to be. And so the governor actually intervened and asked the Water Development Board to terminate that contract. So although the staff we were working with were super excited about the progress that we had made and the initial results that we had presented, unfortunately, we were asked to stop doing that work. But fortunately, in communicating with Mona and Robert, they were interested in the project and asked us to continue that. So that's what we're doing here on this project. Frank, do you want to take over here?
Yeah, sounds good. Hello, everyone. So the start of the project was us identifying what basins and what reservoirs we wanted to model and to generate the synthesized hydrology for. So we chose, 3 major basins: the Trinity, the Brazos, and the Upper Colorado, and within each basin, 5 reservoirs. And we tried to identify quite a wide variety of reservoirs that were larger and smaller, and also reservoirs that were on maybe the main stem of rivers compared to tributaries, maybe the upper basin compared to the lower basin. It's quite difficult, but these were the reservoirs through stakeholder input that we had identified as part of the TWDB project. And associated with each reservoir within the water availability models that we're using is that primary inflow location for that naturalized flow that Barney was talking about. And so those were the points that we were looking at using and starting the Markov-Chain process for. So we're looking at the naturalized flow data set and also the net evaporation data set within the WAMs. So the first thing that was required to generate the synthesized hydrology was to identify transition probabilities. And so this is the probability of, on an annual basis, transitioning from a wet year to a dry year, or a wet year to another wet year, stay the same. And in reverse as well, transition from dry to a wet, or to stay dry from a dry condition. And so we needed to identify those, and those were based on looking at the observed period of record data, so median flow data for each year. If the median flow was above, or the flow for that year was above the median value, it would be considered a wet year compared to a dry year. So we looked historically in developing those transition probabilities. So this is an example of the distribution out of all those dry instances across the historical record for each of the reservoir sites. So this is that dry probability, the probability that if it's a dry year, it'll continue to be dry in the next year. So that if you were to pick a random number between 0 and 1, if you picked 0.5, the condition would stay dry. But if you picked a 0.6, then it would transition to a wet condition. So those were identified for each of the reservoir locations based on the historical naturalized flow data. And then we needed to start building that sequence of years. So we have anywhere from 60 onwards of historical hydrology in the basins. And so we wanted to be able to sample from those individual years. But the first process was to develop just a series of binary wet or dry states. So 1 for wet, 0 for dry. And so we started with a dry state, and then we looked at the dry probability, and then a random value is drawn. And if it reached that probability, or if it was above that probability, it would transition. If it wasn't, it would stay the same. And so that allowed us to build that series of wet, dry states for each of the reservoir sites in each of the basins. From there, let's say, for example, in this particular year, we have 4 reservoirs, and that's that blue box here. So 1 reservoir is dry, 1 reservoir is wet, 1 reservoir is dry, 1 reservoir is dry. So you have 3 dry reservoirs, 1 wet reservoir. Now we need to be able to translate that to historical year to be able to sample, to be able to stitch together historical years. And so we looked at finding the nearest historical analog year, we'll call them. And so in this instance, it was 1991, which is very similar, except for 2 of the reservoirs are flipped. And we used the Euclidean distance approach method to be able to find the one that was closest to that synthesized year that was drawn for that particular basin. From there, we're able to translate that synthetic binary series into actual historical years and actual series of hydrology for each of the basins. So each of the 3 basins, that sequence, annual sequence, where you might start with year 1960, and then you would transition to running year 1948, and so on and so forth. With that series, that kind of concluded the Monte Carlo synthesized hydrology aspect of it, and then we transitioned to being able to run it through the Texas or the TCQ water availability models. So this is just showing the general process I'm going to walk through in a little bit here. The first requirement was to be able to make some fairly minor edits to the existing TCQ water availability models out there. And we utilize the full authorization models for each of the 3 basins. So that represents all permitted water rights and reservoirs in that particular basin. It assumes no return flows. And it also, as Barney was speaking earlier, integrates those naturalized flows to better represent water usage and flows in the basin under those assumptions about water rights diverting at their full authorized amounts. So some minor edits were that we wanted to assume a uniform demand across the year. Normally you have increased demand, at least for municipal use water rights, increased demand over the summer. But a uniform demand we thought was more appropriate for if you were in drought conditions. You would probably have drought restrictions curtailing that use over the summer periods. And then we also represented the demand as its historic firm yield amount. So some reservoirs are permitted for more than their firm yield, and we didn't want to be modeling and showing results initially where the reservoir is frequently emptying out. And I'll explain why a little bit later on. So we first calculated the project's historical firm yield. That's going to be different than regional water planning groups' firm yield. They use different model versions and different assumptions. And then we wanted to model each reservoir individually. It's not a system kind of operation. So each one was run through the 100,000 years of hydrology that was generated earlier in the project. And to be able to do that, we needed to be able to rearrange, kind of reshuffle that historical hydrology based on that sequence. So, it would be reshuffled from, instead of 1940 through 42, it might be 1960, 1948, 1992. And that was run through the WAM for each of the reservoirs. And then with each of the reservoirs, we have WAM results, and we primarily focused on storage levels to be able to classify each particular drought across the 100,000 years. So one of the more important things to water planners is my reservoir nearly empty or empty, right? So we focused on minimum storage across that drought period. So we wanted to be able to classify each individual drought across the whole 100,000 year period based on minimum storage. And if the storage actually did drop to 0, which should frequently happen, we still wanted to be able to uniquely characterize that drought. So we used negative storage proxy by adding up shortages across that period in the drought when the reservoir was 0. And then we used a moving window to be able to identify the worst drought in that window view, to be able to identify nearly 100,000 candidate droughts that we could run firm yield on. But running almost 100,000 droughts and calculating their corresponding firm yields for 15 reservoirs was not really computationally appropriate or smart. So we wanted to use a more intelligent sampling approach. So we used what's called the Latin hypercube sampling to be able to effectively divide up that probability space into equal bins from 0 to 1. And then with each of those droughts put into each of those bins, we randomly selected 1. So we have more confidence in representing the tail ends of that probability distribution. And then we've selected 100 candidate drought events per reservoir across that probability distribution. And then we took those and ran the firm yields on those. So the firm yield process is an iterative one where you slowly decrease the annual demands across the model drought period until the annual demand is fully reliable, which is normally when the reservoir is just above 0 storage during that critical drought period. So these are some of the draft results that were prepared as part of the TWDB project. And this is for the Trinity Basin here. And what we're seeing on the left-hand side is the exceedance probability. And then on the x-axis is the corresponding firm yield. So all the gray dots here represent the firm yields that were calculated from those 100 drought events that were sampled. And then the black vertical dashed line represents that historic firm yield from the historic period of record. And so one way that you could look at this, if we were to look at Navarro Mills, is that there is about a 25% chance that a future drought that was identified from the 100,000 years could have a firm yield that is less than the historic drought of record. So that gives you a bit of a picture in terms of probability of some of these firm yields and how worse they can be, and also how often some of the droughts were producing firm yields that were less than the historic firm yields. The figures on the right are showing the firm yield on the x-axis, and then that critical drought duration, that period from the start of the drought till its most kind of minimum period in terms of reservoir storage. So looking at that spread of how many years compared to the firm yield as well, to provide a little bit more information for water planners. Ongoing work. While we have a lot of useful data already from the TWD project, we're wanting to utilize more recent extended Brazos basin hydrology. And so when we were doing it, it was always pending in terms of its release from PCQ. So it was only through 1998, but they were going to be extending it through 2018. And that really allows us to capture that really new and important drought of the 2010s. And so we want to be able to utilize that new hydrology and rerun that Monte Carlo synthetic process to generate new hydrology. Another aspect that was built into the study that I haven't really talked much about was being able to look at the adjacency of droughts. So what happens if the Brazos Basin at large is in quite an extreme drought? Is the Trinity also in a similar drought? And is the Colorado also in a similar drought as well? And that can be useful for water planners looking at diversifying or looking at other water sources, maybe in a nearby basin. So that is also an aspect that we're going to be looking at. And then we'll eventually be looking to submit a report for publication based on the results of this project. So there's a lot to go through in terms of methodology and showing some of those preliminary results as well. But are there any questions on the study or kind of what we're working on at the moment? We do have some content, as Barney said, afterwards, doing some brainstorming and talking about some other potential projects as well. We wanted to pause here briefly to see if anyone had some additional questions.
Yeah, so as I remember, you've got a 6-month timeline for this. So this project will probably be completed sometime next year, maybe.
We said end of March, is that right, Mona?
Yeah, that sounds right. I mean, for how the contract was run, I was just curious, because you guys haven't really had much time, like you're obviously well into it, but you haven't had much time to jumpstart the finishing the work, have you? Or
No, well, we're not close to finishing yet, but you know, the good thing is
get started.
Yeah, the methodology is all there, right?
Yeah.
What we're doing right now. So I should have mentioned earlier on, we're partnered with a couple of other firms. Richard Hoffpower, who's a WAM guru, is a one-man show out of College Station, studied under Ralph Werbs, and then RTI, who are, well, Jonathan Kebeman in particular is a real stats guru. So he helped define the kind of methodology, and he's actually developing the time series. So he hasn't delivered the Brazos River time series to us yet, the 100,000 years. But as soon as he does, then we'll start working with the WAM to generate that new set of results. And then it's going to be a case of kind of analyzing the findings, summarizing the results, and starting to write it up. So that's kind of where we're at right now. I wanted to mention earlier, and I didn't mention, that we're not trying to recalculate a new firm yield for any of these reservoirs. What we're trying to do is show that there's some uncertainty in the numbers that are being used right now in water supply planning. And a lot of entities, a lot of water planners are already kind of hedging their bets on climate change and in this most recent drought by choosing other terms or other numbers for their reservoir reliability. So there's the safe yield, which is used, and generally the definition of safe yield is a situation where you've got 1 year of reserve supplies in your reservoir through repeat of that drought of record. So instead of the reservoir emptying out completely, you've got 1 year left. But what this is showing is that there's, indeed some uncertainty associated with that firm yield. And then I think it's up to water supply planners to determine what sort of level of risk or uncertainty they're willing to accept for the water supply planning process.
Could you go back to the slide that was showing those preliminary results? And I guess my question is related to what you just said, Barney, which you may have just answered, but it's like how might a water user, water manager, use this? Like looking at Weatherford, looks like they're in pretty dang good shape, but maybe Bridgeport looks a little scary. And I guess, given the safe yield approach that folks have, you could use this to see how much more certainty, perhaps a safe yield. I think some of the regions will use 2 years on reservoirs. What does that get you, I guess, in building resilience?
Yeah, we tried not to be too prescriptive in this approach. We didn't want to tell people that they should adopt the safe yield or, 1 year or 2 year safe yield or tell them how to do their planning. But
exactly,
it does give folks an idea of, whether their firm yield is something that's, perhaps pretty darn good for planning. In other words, it's not likely to be much worse than that in the future, versus something like Bridgeport, where, gosh, maybe you want to take another look at that and, use a different number for firm yield or, that water supply reliability. So we purposely left it open, and that we were trying to kind of shield ourselves a little bit from the potential political firestorm. Obviously, we didn't do a good enough job. But I think the bottom line is there's some super useful information here, and we should talk about providing the raw data in some sort of data portal so people can play around with it. Get their own, run that 100,000 years of flows through their own WAM models and play around with that, perhaps.
So of the 5 examples you've got there, Bridgeport, in quotes, looks the worst, I guess, in terms of like what the firm yield is compared to your analysis. What's going on there? I mean, do you have an idea about why, most of the analysis falls below the firm yield?
So one of the things we started doing with the Water Development Board, but didn't get very far along with, is trying to see if there's any kind of pattern emerging, right? Whether this is smaller reservoirs that are more vulnerable, or ones that are in sort of more on the drier parts of the state, or ones, what is there any kind of clustering? Is there any sort of pattern that we can see in those? And we really didn't get very far with that, Frank, I don't think. We've got 3 basins that are large basins, and they're all adjacent to one another. So I think that makes whereas the reservoirs are kind of spread out throughout the basin. So I think that gives us some good, sort of good geographic spread and good diversity and size of reservoirs to look at, but we don't have any conclusions related to that just yet.
Okay.
I think you could generally, Robert, say that Bridgeport has gotten very lucky historically, right? It's maybe an oversimplification, but if you were to look at the worst years in the historic period of record, they probably didn't all line up next to each other. So this resequencing approach, the Monte Carlo approach, allows you to generate different droughts based on the historic data, and it's showing that they might have those future droughts where more of the really bad drought years are lined up together in series.
And that does look like it's over there by Wizard Wells, but it does look like it's a relatively small reservoir.
Yep.
And you're starting to get, and it's what, northwest of Fort Worth, so it's starting to get much higher evapotranspiration over there as you get west of there. I've been working with a graduate student looking at the firm yield of rainwater harvesting systems, and one thing we've noted is like the size of the tank, the daily use, the roof area, in other words, catchment, reservoir size, has a big control over what type of drought is controlling the firm yield.
Yeah.
So yeah, it could be what you were saying, kind of this might be the smaller reservoirs are perhaps more susceptible.
Yeah, that would be my guess. Smaller reservoirs on smaller watersheds in the sort of semi-arid or more arid parts of the state. But, you'd expect the firm yield of those reservoirs to be lower too. So it's not super straightforward analysis. But the nice thing about rainwater collection is that you don't have the evaporative losses that you have on open reservoirs.
Exactly.
So if you've got a big enough roof and a big enough tank, you can get through some pretty horrendous drought periods.
Right.
Frank, do you want to pull up those other slides if we've got time, if there's nothing else on that? Yeah, so Mona and I have actually had a couple of conversations about other research topics, particularly sort of impacts of climate change on water resources. And so I threw a couple of slides together describing a couple of ideas here. I thought this might be a good opportunity to discuss them. So one of which is on the potential for reservoir reallocation. So this schematic shows a cross-section of a large federal reservoir. And those reservoirs that we have in Texas are almost always multi-purpose. So they'll have a water supply component to it. There'll be a flood control component, and sometimes there's other components as well, like hydropower, for example. But that reservoir is divided up into different regions. So below the lowest outlet on the dam is typically called the dead pool. There's nothing you can do with that part of the reservoir. And then there's a part of the bottom of the reservoir that's set aside for sediment to accumulate over time. And then there's a water supply aspect, but the reservoir is never completely full all the way to the top of the dam if it has a flood control role and responsibility. And so that's what's shown here schematically for an example reservoir. If you go to the next slide, Frank.
Nice visual, Barney.
Yeah, I didn't do that myself. I stole it. I found it online and stole
for
it.
you. Even more impressive. You saved time.
It does look good though, doesn't it? It does show
extra points for saving time.
Yeah. You can see on there, so like that blue line, that blue horizontal line on the dam, so that's typically where a top of conservation pool, or in this case, irrigation pool, is located, right? That's where you'd like your reservoir to be all of the time. If you get a massive rainfall event, that water will fill up the reservoir to a certain amount, and the reservoir and dam attenuate that flow downstream, and so the water is released more slowly than it would occur otherwise, protecting infrastructure downstream. And those dams are all built to withstand, these larger dams are all built to withstand what's called the probable maximum flood. And that results from the probable maximum precipitation. So the biggest rainfall event that you could imagine, or that we deem to be physically possible in the watershed, is what that dam has to be designed to withstand without failing. So all of those dams in the Texas and the US and actually around the world are built for that PMF standard. Next slide, Frank. So what's interesting is the vast majority of those dams in Texas have been built based on the PMF that was estimated in 1971. And HMR 51 basically describes how much precipitation one could expect above these large dams, which is subsequently routed to the PMF, and the design is based on that. But those numbers are obviously old. We've got some new rainfall statistics since that time. We've got radar since that time. We've got lots of good information. And so in 2016, TCEQ contracted with an organization called Advanced Weather Associates out of Colorado to revisit those PMP estimates. And interestingly, they found for large parts of the state that the PMP should actually be significantly lower than the number that's being used. And that's a good thing. Where it's more, then that's perhaps potentially a little bit worrying. But for water supply purposes, where the new PMP is significantly lower than what the dam was designed for, we've got an opportunity to reallocate some of the storage in those federal reservoirs for water supply instead of flood control. And if you go back, Frank, to that previous slide, what that means is that that blue line, the top of irrigation pool or top of conservation pool, we could move that up and effectively increase the storage facility without compromising the integrity of the dam or its purpose as a flood control structure. So that's kind of an interesting opportunity to me. Next slide, Frank. So what we could do, well, let me back up just a little bit. So some states, and AWA are kind of the premier organization for re-estimating PMPs. They've got a bunch of folks. They've done this work in states all over the United States and internationally as well. But what they're working on with some states, not Texas right now, is updating those PMP estimates based on what they're expecting in the future, say 2060 or 2050, based on those climate change models. And so you could potentially generate a table similar to the one you see on the left-hand side of your screen there that shows PMP for that 2050 or 2060 condition. And so it's kind of a two-step process, right? You could update it to 2016, see if there's opportunities for reallocation, and then update it again for the PMP situation in the future. And so, particularly in parts of the state that are fairly arid, or parts of the state where there's really a strong need for water because the region is growing fast or there just aren't any additional supplies available, the opportunity to reallocate some of that flood control into water supply in these major reservoirs seems like a superb opportunity. That water is going to be, because the facilities are already there, that water is going to be much cheaper than it would be otherwise. And in federal reservoirs that have a flood control purpose, there aren't any structures that are built in that flood zone of the reservoirs. You'll recall, like Canyon Lake or Buchanan Lake, there aren't any structures that are built below the top of the flood pool. So, like I said, I think there's a tremendous opportunity there.
So is the change in the statistics due to just having a longer, better record, or is it also reflective of changes that we're seeing due to global warming?
Well, I guess you could argue that both, but I think it's mainly that we've got some additional statistics and we've got some additional models and knowledge about the upper physical limits of the amount of precipitation that can fall out of the atmosphere in certain parts of the state. This happens to be the subject of my PhD, so maybe that's why I'm so excited about it. The traditional approach to estimating the PMP is there's two different ways to go about it, right? One of which is to look at statistics and basically extend those statistics, the probability of rainfall, way out into the future. So a PMP is often being equated to a 1 in 10,000 or a 1 in 100,000 year event. So you can plot the rainfall, plot the extreme rainfall on a Gumbel probability plot and just extend it out to 100,000 years and call that the PMP. But some folks prefer the physical approach, where you look at all of the, the humidity, the atmosphere, the weather dynamics, and estimate what the maximum amount of rainfall. Well, first, the maximum amount of humidity that could be held in a column of air above a particular point, and estimate the maximum amount of precipitation that could possibly occur, including all of the interesting weather dynamics that can occur over the period of time, because the PMP, could be a 6-hour event for a small watershed, or it could be as much as 72 hours for a larger watershed. It just depends on the situation and where that reservoir is located.
Mm-hmm.
Barney, there's a question from Jenna Walker.
Okay, let's look.
Do you take PL 566 dams into account as well?
Yeah, for sure. This would be applicable to any dam that's being built to PMF standards. And the dam safety program at TCEQ has a list of all of those dams that have to meet PMP or PMF standards. And basically it's any, I don't know about any, but most of the ones that have a water supply purpose are built to the PMF standard. And interestingly, they don't all have a flood control purpose, but they still need to be designed to be able to handle the probable maximum flood. Basically, if the dam fails, if the result of a dam failure would be potential loss of life, then that dam has to be built to the PMF standard.
I wonder if Jenna might have been asking, like in a watershed for a dam, if you also have PL 566 dams, are those taken into account with?
You mean on the routing of the floodway?
Yeah.
Yeah, so they
Yeah,
should be.
I'll give some context. Can y'all hear me?
Yeah.
Yes.
So I know in the Lake Waco watershed recently that feeds into the Brazos, there are a bunch of PL 566 dams upstream. And for the most recent rains, there was like 5 to 6 inches of rain up in the watershed, and none of it made its way down to Lake Waco, mostly because of the PL 566, but also with the drought. And so I was wondering if y'all were, taking that into account.
That's actually a great question, Jenna, because a lot of those dams were built, like in this situation you're talking about in Waco, were built to withstand a PMF before there were any other structures in the watershed above. And if they have some ability to hold back floodwaters as well, then you could make a strong case for that downstream reservoir to be reallocated just based on that situation, not because of any changes to the PMP, for example. And that situation happens a lot as well across the U.S. For example, a basin that I've been working with in Oklahoma, Lake Hugo is at the bottom of the Kiamichi watershed, and Sardis was built subsequent to that. Sardis has flood retention capability, so Hugo could potentially be reallocated based on some of those floodwaters being held back by that reservoir that was built subsequently, which is exactly the situation you're talking about. So there's reasons to revisit some of those PMF calculations just for that very reason.
Well, I like this research project because it's like, maybe a little bit of positive news out of a warming climate, where it's like, well, if there is less rainfall, particularly in the drier parts of the state, then we don't have to worry as much about a giant flood, in which case, we can store more of the water. Is the, sort of the dogma is that the rainfalls will get more intense. You hear that from John Nielsen Gammon. He's mapped out that report he did for Texas 2036. He's kind of mapped out where there's been that increase. So is I don't know if you know, but I mean, is the analysis showing that that's not happening in the drier parts of the state?
No, so I really like this table, right? Because it shows, instead of having to look to see what the signs of all the numbers are, it kind of shows you which direction it's going with the cup shape. But there's a similar figure to this for states that are revisiting the PMP under climate change situations where, and there's some preliminary results from John and others in Texas that show a kind of a similar situation. And I don't know if it's a trend on what's already going on or whether it's kind of a different pattern that you would overlay and sort of add them all up and see what the difference is. But there's definitely some parts of the state that in the future will have even less PMP or less magnitude on their PMP, and some parts of the state that we're expecting that PMP to be higher.
Higher, okay.
Yeah. So you'd have to be careful. We'd have to look at the results. If we did this study, I think we would want to work with John Nielsen Gammon and AWA on figuring out where those best opportunities are for those reservoir reallocations, and then only study that part of the state. You know, if it's close, if there's only a change of like 7% or 4% or something like that on the PMP, then it's probably not worth the time and effort. But in some of these instances, you're seeing a change in the PMP of 50%, and that's a ginormous amount of water or additional storage that could be made available for those, you know, those parts of the state. And this, we're looking particularly at zones 7, 10, and 11, which is, you know, it's far west Texas, it's the Panhandle, and yeah, that part bordering on New Mexico. So those are the areas that are there's particularly good opportunity, I think.
And those are also places, as you know, with a lot of need.
Right. Now the flip side to that is there aren't a huge number of reservoirs in that area. But
Yeah.
you know, I think zone 12, I think, is a good one. You know, zone 8 is also, zone 8 would be a particularly good one. That's where Bridgeport is, right? Zone 8 would be one where we're not seeing a reduction in PMPs that are quite so much as those other areas, but there's a huge number of reservoirs there and ones that, you know, help feed the Metroplex. So that might be where the best opportunities in Texas lie. So anyway, that's one idea. John, Frank, do you want to skip to the next one real quick? And I know where it's 10 to 1 and some of us have meetings at 1 o'clock probably, but I wanted to touch on this idea I had as well, looking at reservoir sedimentation. And this is something that I studied quite a bit when I was at the Texas Water Development Board in the surface water division there. All reservoirs fill with sediment, and some of them fill gradually and some of them fill more rapidly. But as you can imagine, as reservoirs fill with sediment, it reduces their holding capacity and eventually will start reducing their firm yield and their ability to supply water. And in fact, you know, this schematic is slightly misleading. In an ideal world, that sediment would drop out in the lowest part of the reservoir where it has least impact on, you know, diversion structures and things like that. But actually what we have is sediment typically will fill up in a reservoir like this. So the day the reservoir is constructed, it already starts to impact the conservation pool and that conservation storage amount. So what I've been wondering about is what the impact of climate change might be to the rate of sedimentation of some of these large water supply reservoirs. If you go to the next slide, Frank. And what the climate scientists are saying is that we should expect, for large parts of the state anyway, we should expect more severe droughts, so longer periods of low or no rainfall, which has an impact on vegetative cover and the roots that hold that sediment in place, of course, but also to expect more extreme rainfall. And if you have a situation where you've had a really bad drought and the vegetation's being compromised, and then you have a really heavy rainfall, that sediment is going to get mobilized quicker than it would do otherwise. So what erosion in the watershed is exacerbated, and that sediment has to be carried somewhere and will typically drop out in one of those big water supply reservoirs. What I'm not sure about is what the extent of that problem might be. If there's some parts of the state that might be more vulnerable than others, or some watersheds that might be more vulnerable than others. And trying to estimate how the sedimentation rate might change across the state as a result of climate change. And then ultimately, perhaps a subsequent phase might be, what mitigation measures could we put in place? Would it be sensible to build, small impoundment structures behind some of these big water supply reservoirs to capture that sediment before it has an opportunity to empty out in the reservoir, sort of PL 566 type structures, Jenna? Or maybe there's other approaches that would be more effective, or just as effective, or in some way mitigate what we expect to see through climate change. When I was at the Water Development Board, we funded a study looking at the cost of dredging reservoirs versus the cost of building new reservoirs. And at the time, and I suspect this is still the case, the cost of dredging was significantly, like 3 or 4 times higher, depending on local circumstances, higher than building new reservoirs. So reservoir sedimentation is definitely a significant issue. It's not something that can be dealt with very easily. And to generate new capacity through dredging, or restore an old capacity through dredging, is a very expensive exercise. And I think it would be pretty interesting or useful to know if sedimentation is going to be worse in the future than it is right now.
Yeah, I don't remember if we talked about it, Barney, but I'm working on a couple of projects now looking at this kind of thing from lake cores, and the signatures are kind of like jaw-dropping, and it's probably going to be worse in Texas, but there's beginning to be a lot of international literature on this. And then the other thing in Texas is the land use change from a population change. That's probably like a really huge deal for Texas, I would imagine.
Well, yeah, there are other changes in the watershed that aren't just climate change related. So, assuming linearity on that rate of sedimentation is probably a false assumption. So,
yeah.
Looking at core samples, that's something that the Water Development Board does actually through the hydrographic survey program. So they estimate the volume of sediment in reservoirs, but you can actually take those core samples and do an isotope analysis to determine what types of events brought that sediment into the reservoir, as well as looking at where the distribution of sediment is within the reservoir as a result of particular rainfall events. So there's all kinds of things that could be done here, and this is something, again, that's interesting to me.
Well, we're probably just about to run out of time. Does anybody have any final questions, or Barney, Frank, do you guys have any final comments?
Yeah, no final thoughts from me on that. I think there's lots of interesting things that could be done. And I feel a disconnect between the climate scientists and water resources engineers and scientists and managers. It's hard to take those climate models and make sense of them when you're trying to manage the water resources of the state, right? There's some translation that needs to take place. So these are kind of the questions that I have.
Based on your talk today, I'd be really interested to have some more discussions about statistics, because if the PDF is changing, then it changes the whole statistical picture. And I've been trying to wrap my head around that, like even if you just leave climate models out of it. But for another day, I guess. Barney, Frank, thank you both so much for your time. Really appreciate you coming here. These are exciting proposals. I'll see if I can have a catch up with Robert about what he thinks.
Yep. Sounds good. I appreciate it.
Thank you, everyone.